set. And then this other mode, which I just mentioned, the discriminative mode, where I want to be able to classify things, make decisions in an environment. And these aren't mutually exclusive. There are engineered systems out there that combine elements of both of them. But typically, researchers work on them as distinct entities. So I want to talk about both of these modes in detail. And let's start with the discriminative AI story, because again, I think that's really where deep learning begins in terms of people becoming interested in it in this most recent sort of surge of artificial neural networks. As I just mentioned, again, the idea is coming back to classifiers where we have labeled objects that we want to categorize. It's supervised machine learning for the most part in both of these modes, in that we have large labeled data sets that we use to instruct the computer on what to recognize. And in the most basic sense, right, we may have a binary classifier that's able to take in some image of a cat or dog, correctly put it into the beginning of the internet. There's never been such a fun fact. And you could generalize this to multi-class classification. There's a bunch of different modes of classification. And what's really fascinating is that early on in the development of today's machine learning, it was believed this problem was a lot easier than the problem of generative AI. And it turns out this is flipped, and we'll see why in a moment. Okay, let's keep going. So as I mentioned, right, none of these ideas are particularly new. What happened about a decade ago is we reached an inflection point on the internet as a source of data, and also in the development of parallel hardware that allowed us to train these very large models. Folks like Hinton knew back in the 1980s that the things we're doing today would be possible, but they were really constrained in that, where do you get the data, right? There really wasn't an internet like we have an internet today, which is this rich source of multimodal data, right? You would have to create these data sets by hand. Not everybody had a digital camera back in the early 1980s, so if you're doing computer vision, you were very lucky if you had a data set of maybe 10 or 20 images. You had enough memory on your computer to process them, all these different things. Now, folks, even in that early era, were paying attention to developments in high-performance computing. We did have supercomputers back in the 1980s, the 1990s, right? I know some folks from the national labs are here, right? You may be chuckling. A lot of advancements in vector processing go back to the sort of 70s, 80s, and 90s. And folks, again, working on computer vision, natural language processing, were kind of salivating at that hardware, but they never got a chance to use it because it was being dedicated for physics simulations and other forms of computation. But they always kind of wondered, what if we had access to hardware like that? What would we be able to do? Well, it turns out what you'd be able to do is linear algebra very, very fast, right? Compute dot products in parallel on very, very large tensors. So by the time you get to the 1990s, you have miniaturization accelerating. So NVIDIA appears, right, as a company. We're all probably familiar with this company because it's one of the most valuable companies in the world as of this week. And NVIDIA is really interested initially in creating graphical processing units, right? This hardware that can render computer graphics specifically for gaming. But they also realized there are other applications. Jensen Huang, the CEO, I think is one of the savviest sort of tech executives. He sort of knew the writing was on the wall for things like artificial intelligence. And they started to try to figure out how to create hardware that would have a dual capability, right? It would still be useful for playing games, but it would also be really useful for processing large amounts of, say, visual data. And by the time the cards are really, really good and can do this, the internet has so much visual data because we all got these devices and we all started taking pictures and videos and uploading them to the internet, that researchers like me had this huge wealth of data. And also large corporations had all of this data, specifically, right, social media platforms. Part of their business was to get users to upload as much content as possible because this was giving them the data sets they needed to do the work they really wanted to do in the realm of AI. Of course, right, we have to measure progress in some way. And so the computer vision community have been developing standardized benchmarks over the years. In 2009, Fei-Fei Li, who is now a professor of computer science at Stanford University, a very, very prominent voice in AI, she was at Princeton at the time. She published a paper introducing a new data set. And it was a remarkable data set in that it was very, very large. It was known as ImageNet, still is known as ImageNet. It was made up of images that were crawled from the public internet. Now, right away, there were some issues with this because of copyright, and so the data set sort of exists as a collection of links, right? So they don't, easily distribute the original data set, the original images. But it had a lot of variation. A lot of different object categories, number one, and object categories that were linked to the WordNet hierarchy and natural language processing. So it was like a rich hierarchical representation of different things that one might find in a real environment. And they also did a really nice job sort of annotating these images. So they would crawl images, they would show these images to workers on a crowdsourcing platform, Amazon's Mechanical Turk, and they would get labels for these images. And so it was this really nice, well-curated data set that was reaching web scale, which we hadn't really seen before. Because as I mentioned, right, there were huge computational constraints and the data sets were very small. And so this became like sort of the new standard in 2009 for evaluating visual recognition algorithms. So again, thinking about that basic classifier I just mentioned, right, cats versus dogs, imagine scaling that up to n number of categories, right? Can you have a model that can successfully label all these things, knowing there's going to be a lot of variation, right? There's going to be variation in texture, color, shape, size, etc. That said, this data set is basically large objects of interest in the center of the image. It's not sort of, as real world as one would want. But 10 years ago, this was seen as being a very difficult task. In fact, it was for the approaches at that time. So some years passed, they start running a competition at various computer vision meetings, and then we get to 2012, and there's a result that's posted which blows everybody's mind. Number one, it was an artificial neural network, and this approach, as I said, had been very sort of computationally constrained. It was largely discredited for various reasons. And all of a sudden, it's back, and it's the best thing. The other approaches that were competing on this challenge were sort of handcrafted, right? So intentionally designed image features, right? More procedurally programmed material, even though there was some machine learning in the classification stage. Trying to extract information from these images to process and classify is very, very challenging. The big advance in this AlexNet neural network is that it was learning features from the images in the training data, and those image features were more expressive than what people were specifying by hand in the past. And this basically changes the entire subfield of computer vision. Everybody pivots to neural networks, and there's just tremendous hype over this advance. Now, calming down and sort of looking at what exactly is happening here, it's a very simple task, right? Image classification. Just label these images. And the metric being used here is error rate, right? How often am I wrong assigning those labels? And even the AlexNet advance, it wasn't like huge, like an order of magnitude more accurate, but it was a pretty good leap in performance. And folks quickly realized by using artificial neural networks and continuing to scale the training data, and a little futzing with the hyperparameters, you could incrementally chip away at this to the point where in 2016 we achieved what was claimed to be superhuman performance because the ImageNet researchers had gauged the accuracy of humans on this same task. And some of the images are a little bit challenging, right? There's some ambiguity in them. And computers were all of a sudden slightly better than people. And then all of a sudden, right, there's this influx in the popular reporting on all of this, of these big claims about we're there, right? Artificial general intelligence may be here, self-driving cars just around the corner, all of these different things. Now, this is what we call deep learning. These are very highly parameterized neural networks. Back, again, like the 80s and the 90s, when a lot of the basic architectures were being formulated, they were typically very shallow because the memory just couldn't hold the number of parameters. This was not as much of a constraint with very cheap memory